In May 2024, a brand new Chinese nuclear attack submarine never made it to sea. It did not collide. It was not torpedoed. It did not suffer battle damage. It sank at the dock, at the Wuchang shipyard, along the brown currents of the Yangtze River. The lead boat of what analysts call the Zhou Class quietly slipped beneath the surface during final fitting out. No missiles fired. No alarms heard worldwide. No official acknowledgement. Just cranes. For massive salvage cranes appearing in June's satellite imagery, hovering over water where a nuclear-powered hull had stood in March. One open valve. One unsecured hatch. $1 billion machine converted into a steel anchor. And here is the question that matters. How does a Navy racing to challenge American carrier strike groups lose a nuclear submarine before it ever leaves the pier? This is not a story about mockery. It is a story about systems. Because the physics that sink a submarine at dock are the same physics that decide survival at 500 feet. And there is one deeper vulnerability exposed here that has nothing to do with valves. We will come back to that. To understand the magnitude of this event, the submarine itself must be understood. The Zhou Class was not incremental. It was ambitious. Chinese naval planners designed it as a next-generation nuclear-powered attack submarine, an SSN, optimized to hunt U.S. carrier strike groups operating in the Western Pacific. The geometry mattered. Reports pointed to an X-shaped stern configuration, 4 control surfaces arranged diagonally rather than in a traditional cruciform pattern. Why? Because X-sterns improve maneuverability in shallow littoral waters. They reduce acoustic turbulence. They provide better control authority during rapid depth transitions. In confined seas like the South China Sea, geometry becomes survivability. But design ambition extended beyond the stern. Intelligence assessments suggested hybridized propulsion experimentation, blending diesel-electric architecture knowledge with nuclear systems integration. This is complex territory. Diesel submarines and nuclear submarines are built around entirely different engineering philosophies. Diesel boats prioritize battery management, snorkel cycles, and acoustic silence during short bursts. Nuclear submarines operate as closed thermodynamic systems. Continuous steam generation, high-pressure coolant loops, reactor containment protocols, redundant safety interlocks. One mistake in a diesel boat floods compartments. One mistake in a nuclear boat can disable a reactor plant. And here is where strategic context sharpens. The submarine was assigned to a yard traditionally specialized in diesel-electric construction. Nuclear complexity demands different safety culture, different tooling discipline, different inspection doctrine. Submarine engineering is not about speed. It is about margin, pressure margin, heat margin, procedural margin. The ocean is an unforgiving auditor. At dock, hydrostatic pressure is minimal. If a hull floods pier side, the failure did not come from ocean physics. It came from human systems. China's naval expansion over the past decade has emphasized production tempo. More hulls, faster commissioning, higher output targets. That tempo creates a structural tension. Industrial quotas versus nuclear safety protocol. And this tension is not theoretical. In 2023, Chinese missile forces faced internal scandal over improperly fueled ballistic missiles, reportedly discovered with water where fuel should have been. Whether exaggerated or not, the pattern is what matters. Production metrics can overshadow inspection culture. Now, layer that into nuclear submarine construction. A submarine at the fitting out stage contains partially integrated reactor systems, electrical distribution panels, sonar arrays awaiting calibration, combat management computers, hydraulic control circuits, flood control valves not yet sealed into operational configuration. An open seawater intake valve during final testing is not cinematic. It is procedural. But water does not care about procedure. The Yangtze River is not clean seawater. It is sediment-heavy, electrically conductive, mineral-rich. When muddy river water enters an unsealed compartment, 3 things happen immediately. First, electronic contamination. Silt bridges circuits. Short circuits follow. Second, corrosion onset. River chemistry accelerates oxidation. Third, systemic inspection, collapse. Every soak system must be torn down and rebuilt. And if reactor components were present, even if inactive, water intrusion into nuclear-adjacent systems creates months of forensic engineering work. Now, add optics. China did not announce an accident. Instead, domestic references vanished. No official imagery. No press briefings. No casualty confirmation. But satellites do not participate in censorship. March imagery showed the hull present. June imagery showed absence. And 4 heavy-lift cranes positioned precisely over its last known coordinates. The salvage signature was unmistakable, which raises the open question. Was this merely an operator error, or was it a systemic indicator? Because history records that even advanced navies are not immune to pure-side accidents. The United States lost the USS Guitarro in 1969 during fitting out due to procedural failure. The difference is not the accident. The difference is institutional response. Before we move forward, consider this. If you were managing rapid naval expansion, would you prioritize production speed or inspection redundancy? Make your strategic call. On paper, the Zhou Class represented momentum. China's naval expansion over the past 15 years has been numerical, visible, and relentless. Destroyers, frigates, carriers, diesel submarines. Hull counts rising at a tempo unmatched globally. Submarines sit at the center of that strategy. Carrier strike groups project power. Attack submarines deny it. If a next-generation Chinese SSN could operate quietly in the Philippine Sea, track U.S. carriers, and threaten from below the thermocline, it changes operational geometry. The math is simple. A U.S. carrier strike group costs over $20 billion when escorts and air wing are included. A single attack submarine costs a fraction of that. If one submarine can threaten a carrier's survivability envelope, cost asymmetry flips. Undersea warfare is not about volume. It is about invisibility. And invisibility is built on 3 pillars: acoustic signature control, reactor reliability, crew procedural discipline. The Zhou Class was intended to signal advancement in all 3. Extern maneuverability, improved pump jet efficiency, refined hydrodynamic shaping. From a distance, it looked like maturation, which is why the dockside sinking matters. Because the event did not occur under combat stress. It did not occur at crush depth. It did not occur during reactor sprint testing. It occurred during controlled, pier side fitting. That means the failure was not imposed by enemy pressure. It was internal. And when a nuclear submarine floods at the dock, analysts ask a different question. If basic compartment integrity failed in calm water, what happens at 400 feet under combat maneuver? That is not mockery. That is systems analysis. This is where skepticism in the public sphere often goes wrong. Some argue this incident proves China cannot build advanced submarines. That conclusion is lazy. China has built operational nuclear submarines before. They operate SSBNs and SSNs. They patrol. The issue is not capability. The issue is culture. Because nuclear submarine construction is less about engineering drawings and more about procedural discipline. Every valve, every hatch, every through-hull penetration is governed by checklists layered upon checklists. Flooding at dock means one of 3 things. A checklist failed, a supervisory chain failed, or inspection authority was diluted by schedule pressure. And this is where production quotas become strategically dangerous. When output becomes the metric of success, margin shrinks. Margin is everything in nuclear engineering. Consider the 2023 missile fueling scandal. Missiles reportedly found improperly filled during inspection. Whether exaggerated or partially true, the pattern signals tension between reporting compliance and meeting targets. Submarine programs under acceleration face similar risks. Now, layer in yard specialization. The Wuchang shipyard historically focused on diesel-electric construction. Diesel boats tolerate different build rhythms. Nuclear submarines do not. Reactor piping tolerances operate at pressures exceeding 2000 psi. Primary coolant loops require flawless weld integrity. Compartment isolation protocols must anticipate catastrophic flooding. Assigning nuclear complexity to diesel tempo culture is not impossible, but it demands aggressive institutional recalibration. And here is the strategic tension. If China's naval ambition is scaling faster than its nuclear safety culture, then production velocity becomes a liability. Before examining how the salvage unfolded, consider this. If you are planning undersea deterrence, is speed your advantage or your vulnerability? Your analysis. Before discussing consequences, one principle must be reinforced. Accidents do not define naval capability. Response does. The United States has experienced its own pier-side submarine disaster. In 1969, USS Guitarro flooded during fitting out in California. Open valves, miscommunication between test teams, water ingress. The boat settled on the bottom of its berth. It was salvaged, repaired, commissioned. The difference was not technical superiority. It was transparency, procedural reform, and institutional memory. American nuclear submarine construction evolved under the discipline imposed by Admiral Hyman Rickover, the architect of U.S. naval nuclear propulsion. Rickover embedded a culture where reactor safety overruled schedule. Inspection authority could halt production. Documentation was sacred. Personal accountability was enforced. Nuclear power at sea is unforgiving. Water intrusion into electronic compartments is catastrophic, but recoverable. Water intrusion into reactor-adjacent systems demands forensic disassembly. And here is the engineering reality. A nuclear submarine under construction contains layered isolation boundaries. Primary reactor compartment, secondary steam loops, auxiliary systems, combat electronics. Even if the reactor was not fueled or active, muddy river water entering control compartments triggers total systems teardown. Electronics exposed to silt cannot be trusted. Acoustic arrays saturated with contaminants lose calibration. Corrosion begins immediately in unprotected wiring bundles. Salvage cranes lifting the hull are not the end of the event. They are the beginning of reconstruction. This is where satellite imagery became decisive. Commercial and military satellites captured the timeline. March, submarine visible at berth. June, absent. 4 heavy lift cranes positioned in a tight geometry above the former hull position. Salvage operations of that scale are not routine maintenance. They signal submerged mass recovery. Censorship cannot erase orbital observation. And in modern strategic competition, perception matters. Undersea deterrence relies on credibility. Credibility relies on procedural trust. Now introduce the deeper issue foreshadowed earlier. It is not the open valve. It is the silence. Because when a nuclear platform incident occurs, international observers evaluate 2 factors. Was there radioactive release? Was there institutional disclosure? To date, no verified evidence supports claims of radiation reaching neighboring countries. Reactor meltdowns produce measurable isotopic signatures. None have been credibly documented in this case. But absence of transparency fuels speculation, and speculation damages deterrence. The United States publicly investigates peer accidents. Safety boards publish findings. Procedural failures are dissected. Transparency strengthens credibility. If Beijing attempts to suppress acknowledgement, it introduces doubt not about engineering, but about accountability. And in nuclear systems, accountability is a strategic asset. Now the narrative turns. Because the true test of naval maturity is not preventing every accident. It is how the system absorbs one. A submarine does not sink because of one mistake. It sinks because a system allows one mistake to propagate. Let's break this down technically. A nuclear attack submarine at dock sits in neutral buoyancy margin. Ballast tanks partially flooded. Internal compartments sealed but accessible for work crews. During fitting out, multiple hull penetrations remain in test configuration. See chests, cooling intakes, auxiliary overboard discharge valves, sanitary and hydraulic through hulls. If one intake valve is opened without internal compartment isolation, water flow begins immediately. The Yangtze River exerts constant hydrostatic pressure. Even at dock, pressure differential exists between outside waterline and lower compartments. Water seeks equilibrium. If the compartment flood control log is not synchronized between teams, for example, one crew performing trim calibration while another tests piping, a single open intake becomes a cascading failure. Submarines are built around compartmentalization geometry, bulkheads, watertight doors, isolation boundaries. But during construction, those boundaries are sometimes temporarily compromised. That is when discipline matters most. Now escalate the technical stakes. Nuclear-powered submarines contain reactor plant monitoring cabinets, racks of electronics controlling coolant flow, neutron flux monitoring, and steam plant regulation. These systems are hardened for vibration and shock. They are not designed for immersion in sediment-heavy river water. Once flooded, circuit boards short. Insulation absorbs contaminants. Relay contacts corrode. Control wiring becomes unreliable. And here is the brutal math. Replacing a single integrated combat management rack can cost tens of millions of dollars. Replacing contaminated sonar arrays? More. Total reconstruction after immersion can approach a significant fraction of hull cost. A nuclear attack submarine often exceeds $1.5 to $2 billion in production value. If 20 to 30% of onboard systems require replacement, the financial hit becomes strategic. Now layer in reactor implications. Even if the reactor core was not fueled, primary coolant piping, pumps, and shielding structures are tightly integrated. If river water infiltrates auxiliary compartments connected via cable trunks or ventilation trunks, contamination pathways multiply. This is not cinematic meltdown. It is systemic corrosion. And corrosion is the quiet killer of naval reliability. Here is where realism must enter. Undersea warfare is unforgiving. Submarines operate in a domain where internal fire can suffocate crew. Reactor coolant leak can shut down propulsion. Hull breach can implode a vessel. No navy is immune to accident. The United States lost USS Thresher in 1963 due to cascading system failures under test depth. The lesson was not superiority. The lesson was institutional reform. Subsafe certification emerged, a program requiring documented proof of every pressure boundary component integrity, every weld traceable, every valve certified, every pipe verified. Physics does not negotiate. Water pressure at 500 feet exceeds 220 psi. If inspection culture weakens under schedule pressure, the ocean will expose it. Now apply cost per kill logic. A Chinese SSN designed to threaten a $20 billion carrier strike group must survive its own construction phase first. If production tempo undermines safety margin, cost asymmetry collapses internally. No adversary intervention required. Now consider strategic debate. Would you prioritize rapid fleet expansion or nuclear safety redundancy? Even if it slows output, your doctrine call. But dominance in undersea warfare is not defined by hull count. It is defined by reliability. And reliability is built in documentation rooms as much as dry docks. Escalation pivot. Satellite imagery did not merely expose the accident. It exposed response posture. For salvage cranes positioned symmetrically over the berth. Heavy lift geometry indicates full hull lift, not minor repair. Commercial satellites can detect hull displacement shadows, crane cable tension vectors, even sediment disturbance patterns. Orbital ISR, intelligence, surveillance, reconnaissance, has turned industrial secrecy into an illusion. Undersea competition now includes space-based oversight. This is not about ridicule. It is about systemic visibility. And systemic visibility reinforces deterrence. The submarine was raised. What remains unknown publicly is the extent of internal damage. 3 possibilities exist. Limited compartment flooding, reparable with component replacement. Widespread electronic contamination requiring near total system rebuild. The reactor-adjacent compromise delaying operational deployment by years. There is no verified evidence of radioactive release. Reactor meltdowns produce detectable isotopes. Regional environmental monitoring has not confirmed such signatures. Speculation without isotopic data is noise. However, even absent radiation, credibility damage carries operational cost. Submarine deterrence depends on uncertainty. If adversaries question procedural discipline, they question deployment readiness. Now examine systemic response. China faces 2 paths. Accelerate output to offset embarrassment. Or pause, recalibrate safety oversight, and reinforce nuclear procedural culture. History suggests long-term naval powers choose the latter. Because undersea dominance is cumulative. A submarine force is not measured by launch ceremonies. It is measured by patrol hours. Patrol hours require reactor uptime, maintenance intervals, crew confidence, systems integrity. One more escalation layer. Modern naval competition is not purely platform versus platform. It is network versus network. A U.S. carrier strike group does not operate alone. It integrates attack submarines, P-8 maritime patrol aircraft, SOSUS-derived acoustic arrays, space-based ocean surveillance, Aegis destroyer fire control networks. Even if a new Chinese SSN achieves acoustic parity, it must penetrate layer detection webs. Undersea warfare is a system of systems contest. And system maturity includes industrial discipline. Now resolve the earlier open loop. The deeper vulnerability exposed was not the valve. It was production culture under acceleration. Technology without inspection integrity converts billion-dollar assets into liabilities. Nuclear propulsion is unforgiving. It rewards patience. It punishes haste. And here is the strategic reassurance. No major Navy scales nuclear submarine programs without institutional correction mechanisms. If China intends to compete long-term in undersea warfare, it must internalize that lesson. The ocean will enforce it either way. A submarine resting on a riverbed is not a strategic defeat. It is a diagnostic event. The Zhou Class incident does not erase China's naval ambition. It does not halt submarine construction. It does not negate industrial capability. What it does is expose the invisible variable that separates rising fleets from enduring ones. Safety culture. Undersea warfare is unique among military domains. Aircraft can abort. Ships can retreat. Satellites can adjust orbit. Submarines operate inside pressure envelopes that tolerate zero negligence. At 400 feet, ocean pressure exceeds 170 psi. At 1,000 feet, it surpasses 440 psi. every weld, every valve, every gasket becomes a life support component. This is not symbolic. It is thermodynamics and structural engineering. Nuclear propulsion multiplies that responsibility. Reactor cores demand thermal stability. Coolant loops demand integrity. Control rods demand absolute mechanical reliability. And credibility in nuclear navies rests on one principle. Transparency in failure produces strength. Secrecy in failure produces doubt. The United States learned this through tragedy, from USS Thresher to USS Scorpion, and institutionalized reform through subsafe and rigorous nuclear oversight. Inspection authority can halt production. Documentation overrides schedule. Accountability overrides embarrassment. That is not moral positioning. It is survival logic. Now, widen the frame. Global naval competition is accelerating. Hypersonic missiles, unmanned undersea vehicles, AI-assisted sonar processing, space-based ocean surveillance. Future dominance will not belong to the nation that launches the most hulls in a calendar year. It will belong to the nation whose systems survive stress. The Zhou Class sinking forces one strategic question. Can rapid expansion coexist with nuclear-grade procedural discipline? If China answers that question with reform, this becomes a footnote in a longer naval ascent. If it answers with concealment and acceleration, the ocean will continue auditing. Because water pressure does not care about political narrative. It only cares about margin. And margin is built slowly. Now consider the broader competition. Carrier strike groups operate inside layered networks. Submarines operate inside acoustic webs. Space assets watch shipyards from orbit. Industrial culture has become a domain of warfare. In that domain, credibility is a weapon. If you trust engineering over headlines, stay here. This channel analyzes conflict through physics, geometry, and systems integration. Final strategic question. Is the future of naval dominance decided by fleet size or by institutional discipline? Your analysis.